There's only 3 questions left for capacitance, so I'll go through that and then we'll just go through with your communication chapters after that. So you look at page 37 of your electric field and communication chapter. This one will be this one. All right, this one is explain what is meant by the capacitance of a parallel plate capacitor. So you would have encountered questions before that ask you to define capacitance. So capacitance, I mentioned to you that there are actually 2 kinds of capacitance questions. The one which is a general definition of capacitance, and another which is a very specific definition of capacitance. So you see this one here, in the other questions that you have done so far, they only ask you explain what is meant by capacitance. So if they ask you what is meant by capacitance, this one is just simply ratio of charge to potential. Yeah, that is ratio of charge to potential, and that was only 1 mark. Okay, but here they ask you what is meant by capacitance of a parallel plate capacitor. This is the most specific definition, and now it's worth 3 marks. So whenever you see this kind of questions, you need to be a bit clearer on what kind of capacitance is it asking for. If they're asking for you explain what is meant by capacitance in general, this one is your general definition, ratio of charge to potential or potential difference now. Okay, but if they ask you capacitance of a parallel plate capacitor, then you have to say this one is the charge stored on one plate of the capacitor per unit PD applied across the plates of the capacitor. All right, because if you're talking about your capacitor, if you have a charge of negative Q coming here, this plate will become negative Q. And then if you have a charge of negative Q repel away, this plate will become positive Q. So strictly speaking, the charge that is seemingly stored on your capacitor here is actually just Q itself. Okay, so charge stored on one plate of capacitor per unit PD applied across the plates of the capacitor. Okay, so this one is the definition and it's worth 3 marks. Okay, so this part is okay. Right, then you look at part B. Part B talks to you about a parallel plate capacitor C is connected into a circuit as shown in figure 7.1. All right, so they tell you that when switch S is at position X, the battery of electromotive force 120 volts and negligible internal resistance is connected to capacitor C. When switch S is at position Y, capacitor C is discharged through the sensitive emitter. The switch vibrates so that it's first in position X and then moves to position Y and then back to position X 50 times per second. Actually, we are under the capacitance worksheet, page 37. Okay, we actually went through part A already. We're now doing part B1. Okay, right. Okay, so back to this one here. The switch vibrates so that it's first in position X and then moves to position Y and then back to position F 50 times per second. The current recorded on the emitter is 4.5 microampere. Find out the charge in coulomb passing through the emitter in 1 second. All right, they want the charge through the emitter in 1 second. They already told you that the current recorded in the emitter is 4.5 microamps. Okay, what they mentioned to you here is that your switch can alternate between position X and position Y. If it's at position X, your circuit looks like this. If it's at position Y, your circuit looks like this. You can actually split this circuit into 2 separate circuits. One at position X, one at position Y. When it's position X, this one you understand it as the capacitor is charging up. Okay, but then once it's at position Y, your capacitor now being fully charged will now start to discharged through your emitter. So here, you can say that your fully charged capacitor is discharging through emitter. This is what actually happens now. When it's at X, capacitor charges up. When it is at Y, your capacitor, now being fully charged, is discharging through your emitter. And they tell you that the current that's recorded inside your emitter right now is 4.5 microamps. So they're interested in knowing how much charge has actually passed through that emitter in 1 second. All right. So you know that current is actually rate of flow of charge. Okay. You know the current is 4.5 times 10 4.5 times 10 power minus 6 because it's 4.5 microamps. The time that you're considering is just 1 second. So you will get the charge flowing as 4.5 times 10 power minus 6 coulomb. Just like that. All right. Okay. So there's the amount of charge flowing. Then after that, the next thing they ask you is, what's the charge on one plate of the capacitor each time that it is fully charged? Okay, what is the charge that is being stored on one plate of the capacitor each time it is fully charged? Okay, so when you are at position X, that is where your capacitor is charging up. When your switch is at position X, your capacitor is connected directly to your voltage supply. Your voltage supply will actually charge out your capacitor. So what was mentioned to you here was that your capacitor will stop charging. Capacitor stops charging when its PD is equal to supply PD. All right. Generally speaking, your capacitor, when it becomes fully charged, it will, when it becomes fully charged, the PD across it must be equal to the PD of the voltage supply is connected to. So like in your case, when this one becomes fully charged, I know that the PD across it must be equal to the PD of the voltage supply. It must be 120 volts. Okay. So what the question is interested in knowing right now is how many times, what's the charge that is actually stored on your capacitor in 1 second. Okay, sorry, not in 1 second. They are interested in knowing what's the charge on one plate of the capacitor each time it is fully charged. So you can think of it as when your capacitor is charging up, a charge of Q is flowing. Okay, it is flowing. A charge of Q is flowing to one end of your capacitor. Then the same amount of charge is being repelled on the other end of the capacitor. Okay, they're interested in knowing what is the charge that is stored in one plate. Okay, right. So that's one thing here. Now, if you know the PD, if you know the capacitance, you could easily find out the charge because you see C is equals to Q over V. Capacitance is equals to the charge over the PD. But here you only know the PD. You do not know what is the capacitance. And Q is what you want to find. So you're missing one information here. You cannot use C equals to QV to find the answer here now. You have to do it another way. So the only way you can do this is by referring back to what you've just found out, what was just mentioned just now. They tell you that your switch is vibrating so that it is at position X, then to position Y, and then back to position X 50 times each second. So you consider this, you move to X 50 times per second. When you are X, your capacitor is charging up, isn't it? So if your case here is that they say that you move to X, from X to Y back to X in 50 times per second, that means your capacitor is charging up 50 times per second. So to put it simply, you can just think of it as this now. switch is at x 50 times, is at position x 50 times per second. That would mean that capacitor charges up 50 times per second. All right. Based on this information here, you know that your switch goes to x 50 times per second. That would mean that your capacitor charges out 50 times per second. Now, you already know that in 1 second, you already know just now that when your capacitor becomes fully charged here at switch position X, once it goes to switch position Y, your capacitor will fully discharge. It will discharge through the emitter. Meaning to say, when you first charge up here, you store a charge of, say, Q here. When you go to switch position Y, whatever charge Q that you store here will be discharged through the emitter. So whatever Q you have here would eventually be discharged through the emitter. Okay, so here just now you already did something related to this where you say that in 1 second, total charge is 4.5 times 10 power minus 6 coulombs. Okay, the charge is 4.5 times 10 power minus 6 coulomb. All right. So now, if you're really just interested in that one time that your capacitor is charging out and how much charge is stored, what you can just do is that you can just say that if you want to find the charge stored by capacitor, charge stored by capacitor, it will be 4.5 times 10 power minus 6 divided by 50, giving you 9.0 times 10 power minus 8 coulomb. Okay, because you know that when you are at your switch is at position X 50 times per second, that means your capacitor will charge out 50 times per second. All right, but in that 1 second, you know that the total charge that has been stored by the capacitor is 4.5 times 10 power minus 6, because you know that whatever charge that was stored by your capacitor, it will eventually be discharged through your emitter. And you found out that in 1 second, the total charge that was discharged from the capacitor is 4.5 times 10 power minus 6. So if you want to find out the charge stored by the capacitor when it charges each time, you take this, divide by 50. That is the idea here. Okay, so maybe I better just write some other explanation here. In 1 second, total charge is 4.5 times 10 power minus 6. You can think of this one as total charge stored by capacitor in 1 second. Okay, in 1 second, the total charge through the emitter was 4.5 times 10 power minus 6 coulomb. This one is also the total charge stored by the capacitor in 1 second. So you want to find out what is the charge stored by the capacitor each time it charges. Each time it charges, you just take this, divide by 50, because in 1 second it charges back by 50. It charges 50 times. Okay, so that's why your answer looks like this. Now here I've written it like this now, but depends on which one you are. You can use this method. I mean, you can copy this or you can copy this now, whichever is easier for you to understand. Okay, here I say in 1 second, total charge is actually the number of times the capacitor becomes fully charged multiplied by the charge stored on the capacitor. So Q total is NQ, Q is Q total over N, then you get this. It's basically telling you the same thing, but I think for some of you, you might prefer this. Okay, right. So if that one is fine, then after that, they now ask you, find out the capacitance or the capacitor C that you have used. So as I mentioned to you just now, that capacitor that you have here, when it becomes fully charged, the voltage is going to be same as the supply voltage. And now in that question that you've just recently done, you've just found out what is the value of Q. Q is 9 times 10 power minus 18 coulomb. So now you have Q, you have V. You can straight away find out what is your capacitance value already based on this equation for capacitance, where C is equals to Q over V. So if you just take C is Q over V, this is what you get. 9 times 10 power 8 divided by 120, you get 7.5 times 10 power minus 10 farad. Okay, then you get the answer. Alright, so you get the answer there. Then after that, if you just go on to the next question, they will ask you now. Now you have a second capacitor having a capacitance equal to that of capacitor C. Alright, which is now placed in series with capacitor C. Suggest and explain the effect on the current recorded on the ammeter. Okay, so based on what you have here just now, they tell you now you have another capacitor whose capacitance is equal to that of your capacitor C that's now placed in series with capacitance, that's now placed in series with the original capacitor. Suggest and explain the effect on the current recorded on the ammeter. So the easy way to look at it would be based on this one. You can just think of it as this. At switch position of X, the original one was this. This is capacitance C. Now you go and put another capacitor whose capacitance is equal to this capacitor, but you place it in series. So if you add another capacitors in series, and let me use a different color, this will now become something like this. Okay, you have another capacitor whose capacitance is equal to the original one, but you place it in series. Okay, so now when you look at this one here, and I try to simplify it into a single equivalent capacitor. This is akin to me saying that I have a capacitor whose capacitance is actually C over 2, right? This one is capacitors in series. When you have capacitors in series, the total capacitance is actually similar in expression to resistors in parallel. If it's in series, the expression is same like resistors in parallel. So this one would be 1 over C total equals to 1 over C plus 1 over C, which actually gives you C over 2. That's why I can say it's like this. All right. Okay, so whatever charge that is being stored here eventually will be discharged through my ammeter when it goes to switch position Y. Okay, originally X is where your capacitor start charging out, at switch position Y is where your capacitor will start to discharge. The charge that is discharged is what you see as current there. Okay, so now you look at this one here. This one here was already mentioned to you that your voltage supply is 120 volts. It won't change, okay, because you did not change anything here. Now, in your case here, I mentioned to you when your capacitor becomes fully charged, the voltage will be same as your voltage supply. The same goes with this one too. If I put in another new capacitor that is in series with the original one, when these capacitors become fully charged, the total PD must also be 120 volts. Okay, when they become fully charged, they must also be total equals to 120 volts. Okay, so now if you just look at this one, C is equals to Q over V. If my PD is constant, that will mean that capacitance is proportional to Q. All right. Now, when I go from here to here, this one was originally C. This one now becomes C over 2. You will notice that the moment you add another new capacitor, you're actually causing your total combined capacitance to drop by half. So that means your charge stored would drop by half also. So if your charge stored is dropped by half, that means your current will also be half because I is equals to QT. If your Q drops by half, your I will obviously drop by half. So hence your answer is like this. The total capacitance is half, causing the total charge stored to be half. Therefore, your current will be half. Hence your answer being like that. Okay. So that is for this one. If you're okay with that, then you can also move to page 39, which is just 1 or 2 pages away. All right. So page 39 would be on this one. Let me just have a look at it. Okay, page 39 would be this June 18 P42. Okay, this one would be question 6. Right, so if you have a look at question 6, that one should be this one. Okay, right. Okay, now what is meant by capacitance of a parallel plate capacitor? This one I didn't mention to you already. Whenever you see the definition of capacitance, just make sure whether it's a very specific definition or a very general definition. Okay, here they're asking you about what is meant by capacitance of a parallel plate capacitor, and it's worth 3 marks. So you know you're talking about this already. The charge stored on one plate of capacitor per unit PD applied across the plates of the capacitor. Okay. If you have written capacitance as simply ratio of charge to potential or PD, this one won't be accepted. I mean, you probably only get 1 mark lah, but the other 2 marks you won't get. Alright, because this is strictly speaking for the general definition of capacitance. You have seen that question before. The ones when they ask you explain what is meant by capacitance itself. If it's asking you to explain what is meant by capacitance, then you say this ratio of charge to PD. But here it's not asking you that. It's asking you capacitance of parallel plate capacitor, carrying more marks. So you have to write something like this. Okay. So this one just copy from the notes and you should be fine. All right. Okay, then after that, if you look at part B, part B is three parallel plate capacitors, each have a capacitance of 6 microfarad. Draw circuit diagrams, one in each case, to show how the capacitors may be connected together to give a combined capacitance of 9 microfarad and 4 microfarads. Okay, so this one doesn't really need you to do much. They've already set the things here for you. You're only supposed to use 3 parallel plate capacitors, each one having 6 microfarad. Okay, so how You have to do trial and error to find out which one will give you total capacitance of 9, which one will give you total capacitance of 4. So in your case here, if you want to have 9 microfarad capacitance, you can just draw it like this. Okay, now the part here where you have a battery, you don't generally need to draw that. If you want to make your drawing a lot simpler, you can just draw it as this. You can just draw your one like this without drawing the battery. You can just draw it like this, where you have the 2 circles there at the end there. This one will tell us that this is the connection to your battery. Okay, so you do try and error, then you see, you can check whether this one gives you 9 microfarad. In general, there's only 2 things you can do. Either you connect the capacitors in series, or either you connect the capacitors in parallel. Okay, yes, now okay, even if you draw this or you draw this, the marks will still be same. Okay, they're not really that bothered about how you draw the battery. They're more bothered about how you draw the arrangement of your capacitors. So if this one here is 6 microfarad, 6 microfarad, and this one is 6 microfarad. Okay, this one here you can try and see whether it works out to 9. This one, you know that you can simplify the parallel one first. If you simplify the parallel one first, this one is connected in series, it will be akin to resistors in parallel. So when you add it out, it will be, if it is talking about capacitance in series, sorry. This one will be 1/6 plus 1/6 power -1. It's actually just going to give you 3. Okay, this one 3 microfarad, this one 6 microfarad. Now, this one you want to add it up together. This one is resistors, this one is capacitors in parallel. So how you will add it up is like resistors in series, where you can just add them up together. So this one here, your C total is actually just 3 plus 6, giving you 9 microfarad. This part here is for this one. Okay, so this can simplify to this can simplify to this. So you get 9 microfarad. Then after that, you have this one here. You want it to have 4 microfarads. This is the connection that you will use. Okay, 2 capacitors in series, sorry, 2 capacitors in parallel, and then 1 capacitor in series. Okay, so the easiest way I can just tell you now would be to do something like this. If you just draw it like this, I tell you that this one is 6 microfarad, 6 microfarad, 6 microfarad. This one will simplify to, you can clear off the parallel one first. If they are in parallel, you treat it like you would resistors in series. So this one will become like this. This one is 6. If I treat this like resistors in series, this one will become 12. Now I want to simplify this into a single equivalent capacitor. What is the total capacitance here? Because they are connected in series, I need to treat it like a would resistors in parallel. So this is 1/CT, 1/12 plus 1/6. Then my CT would be 4 microfarad. Okay, so you get this. Okay, so it's just try and error. You try and see what happens when you connect 2 in series, then the other in parallel, or what happens when you connect 2 in parallel, then the other in series. Okay, so but in general, you can say this now. If you want to increase capacitance, you need to connect your capacitors in parallel. because I mentioned to you, you connect capacitors in parallel. When you want to add it up, it's like resistors in series. So your capacitance will tend to increase. But on the other hand, when you have capacitors connected in series, you would add it up like you would resistors in parallel. So your capacitance is actually decreasing. Okay, so that part is fine. Okay, then you look at part C. Two capacitors or capacitances, 3 microfarad and 2 microfarad are connected in series with battery or electromagnetic force 8 volts as shown. Okay, calculate the combined capacitance of the capacitors. This one shouldn't be an issue. There are capacitors connected in series. You treat it like you would capacitors. You treat it like you would resistors in parallel. So total capacitance will be 1 over 3 plus 1 over 2, giving you 1.2 microfarad. So this part is okay. Now use your answer in 1 to determine the capacitor, to determine for the capacitor or capacitance 3 microfarad. This one here, the charge on one plate of the capacitor, the energy stored on one of the capacitor. So this circuit that you have here can be simplified to this. All right, maybe it's better if I just withdraw it out for you. The easiest way to do would be to do something like this. This one here was your 3 microfarad, and then this one here is your 2 microfarad. This can be simplified to this, right? I know that this one is 8 volts. Okay, now the questions ask you what is the charge on one plate of the 3 microfarad capacitor. Now you will realize that if you simplify this to a single equivalent circuit here, whatever charge that is stored on your single equivalent capacitor, on your resulting capacitor, is actually the same charge flowing through here as well as here. Because this is similar to this, whatever charge that I have flowing through here is actually the same charge flowing through each of the capacitors. So it will be the same Q that is flowing. What I'm interested to find out is the Q on 3 microfarad capacitor. So the way to do that would be to simplify it first, find out what is the total charge that is being pushed through the circuit. The charge that is being pushed through the circuit is actually the same charge pushed through the capacitor itself. Okay, that's why here I wrote it here as for capacitors that are connected in series, the charge stored in each capacitor is actually equal to the total charge stored in the circuit itself. Right? Total charge stored in circuit is actually the charge stored in each capacitor. That's what this statement here is supposed to mean. It'll be easier to see if you refer to these two diagrams. Okay, total charge stored in the circuit is actually the charge stored in each of the capacitors. Right? So you use C equals to QV for this circuit. You find out what is Q. That Q here is also the Q here. So you get your answer is 9.6 microcoulomb. Okay, so you get that answer. Then after that, subsequently, they ask you to find out what is the energy stored in your capacitor. So this one here, if you know the charge and you know the capacitance, you can just straight away use this. Energy stored by a capacitor is either half QV, half CV square, or half Q square over C. It's always these three. Alright, which one you want to use depends on the information you have been given in your question. you've already found out what is you already know the capacitance of your 3 microfarad capacitor. You already know the charge that is stored in your 3 microfarad capacitor. So you can actually use half Q square over C. You won't be using the first one, neither will you be using the second one, because you do not know what is the PD. Like in your case here, I know that the supply voltage is 8 volts. This one only tells me that the total PD across the two capacitors is actually 8. If this is 8, all I know is that the total PD of this one and this one is 8 volts. But I do not know what is the PD across the 3 microfarad. I do not know what is the PD across the 2 microfarad. I only know that this plus this will give me 8. So here, you actually do not know what's the PD here. You don't know what's the voltage here. So you can't use this straight. Unless you purposely find out what is V, and then only then can you use this. But that one is just an extra step. So it's much more straightforward if you use half Q square over C, because you already know both those values. Okay? So if you're okay with that, then you go to the last one before I go to communication. This one, the last one for you is page 30. Okay, this one is the one that is a bit difficult. No. Okay. Right, so just now for that question, make sure you get your answer as 1.54 times 10 power minus 5 joules. If you're okay with that, then you can move on to page 30. This is your last capacitance question. All right, just have a look at page 30. It's something related to the switch again. Right, okay, page 30. This one is November 17 P41. Okay. This one will be now. Let me see which question is it. Question 6. I think I overshot it. Okay, right. Two capacitors P and Q, each of capacitance C, are connected in series with a battery of EMF 9 volts as shown. The switch S is used to connect either to capacitor T, also a capacitance C, or to a resistor R in parallel with capacitor P. Okay. Switch S is used to connect either to a third capacitor T or capacitance C or resistor R that's in parallel with capacitor P. Okay, right. So now they tell you switch S is in position X. Calculate the combined capacitance in terms of C of the 3 capacitors. So same thing as before, this is a bit similar to that other question that we've done just now. Your switch can be in 2 different positions, either it's at X or it's at Y. If it's at X, your circuit would be this one. But on the other hand, if your circuit is at, if your switch is at Y, your circuit will be this one. Okay, so it changes accordingly, right? So what you do now is that they tell you your switch is at switch position X. Your switch is at position X. This is how it will look like. Okay, right? You have capacitance C here. Capacitance C, capacitance C. Wait, maybe I choose a different color. Find the combined capacitance. Yeah, so your capacitor here has capacitance C. This is a symbol used to represent it. Okay. So what is the combined capacitance in terms of C of the three capacitors? So if you are switch position next, this is how your circuit looks like. So you want to simplify it. Now when you want to simplify it, you try to solve the part that is in parallel first. If this one is connected in parallel, when you want to add it up, you treat it like you would resistors in series. So the capacitance for the parallel portion is just C plus C. Okay. So your circuit now becomes something like this. Okay. Where this one is now C, this one is 2C. So now if you want to simplify this again, find out the total capacitance now, because this is connected in series, you treat it like you would capacitors in parallel. So your total capacitance now will be 1 over CT plus 1 over C plus 1 over 2C. Okay. What I've done here is actually like a shortcut like that. I know that I want to simplify this one first, so this is C plus C, and then it becomes this. And then when I want to simplify this again, I treat it like I would resistors in parallel, so it'll be 1 over C plus 1 over 2C, eventually giving me my total capacitance of 2 over 3C. Okay. So my total capacitance is 2 over 3C. Now, the next one here will be the potential difference of capacitor Q. Find out the PD across it and then explain your working. Now, your capacitor Q is this one. This first capacitor here. They want you to find out the potential difference across your capacitor Q. Explain your working. Now, if you look at that circuit just now when you switch position X, this is how it originally looked like. If I simplify the parallel one, it will become like this. And then if I simplify this one, it will become like this, right? So the thing here will be that if you look at this circuit as a whole, whatever charge is stored, whatever total charge is stored in the circuit will be the charge that is stored in here and also the charge stored in here. Okay, you can work backwards by looking at this. If this is now the single equivalent circuit, whatever total charge is stored in the total in the total equivalent capacitance, that charge will be the charge here and also the charge here. Okay. Then after that, this parallel part here, if I break it again into the original, according to the original diagram, this one here, when I break it to the original diagram, this one will be Q over 2, Q over 2. Why is it that this one is Q over 2, Q over 2 is because they both have same capacitance. So I know that here, the capacitance in parallel, once I break them back to the original component, I will have equal charge split between them because they have same capacitance. Okay, but the one here still remains at Q. The one that you're trying to find now is actually this one. Okay, you're still trying to find this one. You're not doing this one, you're doing this one. This is your capacitor Q, labeled Q. So to find the charge, this one they're not asking you to find the charge now, they're asking you to find the potential difference. So the working will be something like this. They tell you that the charge stored in capacitor Q is the same as that stored in the combined capacitance. The charge stored is the same. This Q and this Q are the same. So if I apply the equation C equals to QB, Q is equals to constant here. So capacitance is actually inversely proportional to V, where VQ over VT is the same as 1 over CQ over 1 over CT. So my CT is my total capacitance. My CQ is the capacitance of capacitor Q. It will be 2 over 3C over C. My VT is 9. My total voltage is 9. So I get the answer is 6. Okay, this is the way to solve this question. You cannot find out directly what is the PD here. Can you? No, you cannot. Yeah, you can't find out directly the PD here. This is the only way to do this question now. Okay, you have to identify that whatever Q that is flowing here is the same as the Q that is flowing here. So you apply C over QV for this part, and for this part, you get the relationship. Capacitance is actually inversely proportional to voltage, or voltage is inversely proportional to capacitance. So VQ to VT is actually CT to CQ. You know CT, you know CQ in terms of C. Then you know VT also. VT is actually your total voltage. So you get your answer as 6 volts. Okay? Then you get this answer. Right? So this one is your answer for this. Then after that, you look at part B. Now, switch S is now moved to position Y. State what happens to PD across P and across capacitor Q. Okay? What will now happen to the PD across capacitor P and Q? Capacitor P is this, and then capacitor Q is this. Now, for our case here is that your switch is no longer at position X. Instead, it's at position Y. Okay, it's at position Y. If it's at position Y, how would your circuit look like? It will now look like this. Okay, capacitor Q, capacitor P. Once it's at position Y, you are no longer connected to this capacitor, you're connected to the resistor. This is how your circuit looks like. Okay, now when you were at switch position X, the one thing that you should realize is that your capacitors are charging up. They are connected to your voltage supply. So your voltage supply will continuously push charge to charge up your capacitors here. Okay, this one when it was at switch position X. Now when you go to switch position Y, where your circuit now becomes like this, your capacitors here you need to realize is already fully charged. Okay, they are already fully charged, and since they are fully charged, your total PD here must be equals to the PD of your supply voltage. Your supply voltage has 9 volts. So these two capacitors are fully charged already. Okay, your two capacitors are fully charged already. The total voltage must be equals to 9. Alright. In the previous question, you already found out Q is 6. Okay, in the previous question, you already found out that Q is 6. Capacitor Q is 6 volts. So likewise, this one must be 3 volts. Okay, so now here's the thing. Once you go to switch position Y, this one, as I mentioned, was fully charged. This one, as I mentioned, is fully charged. Once you go to switch position Y, where you now have your resistor here, what will happen is that your capacitors will start to discharge through your resistor. Both of these capacitors will start to discharge through your resistor. Okay? In your case, current will actually flow from capacitor Q to resistor R here, and then current will also flow from capacitor P to the resistor here. So both are actually discharging through your resistor. Okay, now when they're both discharging through your resistor, this one here will continuously lose charge. Its PD will drop to 0. But then this one here, you will see that, yeah, this one is discharging to the resistor. By right, its PD should drop to 0 also, right? But here you do not have that case because you see, you still have connection to the 9-volt voltage supply. At the same time that your capacitor is discharging, this capacitor is discharging, you also have current coming from here, from your voltage supply to here. So it is charging up your capacitor. So this one here, you can just think of it as charge is moving from supply to capacitor Q to charge it as it discharges through resistor. Okay, so this one was fully charged, this one was fully charged. This and this will discharge through your resistor. This one, it loses charge. This one, it also loses charge. But for this one is a bit special. When it lost charge, it's also still receiving charge back from your battery. Okay, so but the charge that you receive from your battery, it will not go into this one because here your charges are moving in like this, moving out like this. So it is preventing any charge from going in. So in your case here, the charge from your supply will only go to here. It will only keep going to here, but it won't go through here because here is already discharging out. Here you discharge out, your charge come back to replenish. Here you're discharging out like this, your charge is coming here, but it cannot go in because you're discharging in this direction, opposing the direction. Okay, so eventually what you'll see is that this one will fully discharge to 0. This one will discharge but at the same time it's being charged. Eventually you charge back out to 9 volts. Okay, so here when they ask you what happens to the potential difference across capacitor P and across capacitor Q, you will say that capacitor P, the potential difference decreases from 3 volts to 0, whereas for capacitor Q, the potential difference increases from 6 volts to 9 volts. Okay, so if I want to write it out, what can I write here? Maybe I just write something like this now so it's easier to see. Both capacitors discharge through resistor. They lose charge and hence PD. Okay, then you have to say that, however, capacitor Q is still able to receive charge from voltage supply. So it charges back up. Okay, then capacitor Q capacitor P is unable to receive any charge from voltage supply, so it discharges completely. Okay? Maybe this one will make it easier to say. Both capacitors will discharge to resistor. They lose charge and hence PD. Maybe I better write this now. Initially, both capacitors will discharge to resistor. They will lose charge and hence PD. However, capacitor Q will still receive charge from the voltage supply, so you will charge back up. Capacitor P is unable to receive any charge, so it will discharge completely. Okay, so when it discharges completely, your voltage, your PD will become 0. Maybe I use a different color. Your PD becomes 0. Here, when your capacitor charges back up, your PD becomes equal to voltage supply. Okay, so this one will explain why this one capacitor Q will increase from 6 volts to 9 volts. This will explain why capacitor P, the PD will decrease from 3 volts to 0.